In our next example, we're going to take a look at supersonic aircraft. In particular, we're going to look at standing oblique shock waves on the leading edge of the aircraft. So what this looks like is the following. So if you have an aircraft, this has some sort of nose like this, and you have some sort of region like that. So on the leading edge of the aircraft, if you're going at supersonic speed, you're going to have a shock wave. So the shock wave is going to come out at some angle like that. So the faster you go, the tighter the angle collapses to the frame of your vehicle. So the angle between this line and the shock wave is called beta. So beta is called the wave angle. And what a shock wave is it's basically a discontinuous change in atmospheric pressure. So the reason that there's a shock wave in front of a supersonic aircraft is that, by definition, the supersonic aircraft travels faster than the speed of sound. So if you're traveling faster than the speed of sound, an interesting thing happens. And to see that, let's start with slower than the speed of sound. So if you're moving slower than the speed of sound, so let's say, you're here and you're moving slower than the speed of sound. If you say something, the sound can move forward. So any disturbance or any noise you make is going to propagate ahead of you upstream, because sound is moving faster than you are. So if you say something or make a noise, or if you're driving a car, people can hear you coming. Now, as you travel faster and faster, you're catching up to the speed of sound. So at the speed of sound, you are traveling as fast as sound itself, which I think is 343 meters per second. I don't have it on me, but I think that's what the value is. You'll fact check me, Google it, but I think sound travels at 343 meters per second. We can take a quick look. Speed of sound. 340 meters per second at sea level. Okay, close. 340. 340 meters. Did that say 340.3? 340.3. So I didn't. Okay, so I must have. When I said 343, I was remembering that 3 there. A long time ago since engineering, but I still remember the speed of sound. So 340 meters per second, and so if you're traveling at 340 meters per second and you're making noise, there's a wall in front of you where the noise that you emit is traveling at the same speed you are. So imagine like you're always right behind the sound wave. So if somebody's ahead of you, they'll see you. So here's an observer, they see you, but they can't hear you because you're traveling as fast as the sound. So the sound wave that you made from back here or from over here is always right in front of you. So they can't actually hear you until you actually catch up to them. And in fact, all of the properties of the ambient air are normal. So sound itself is a change in pressure. So if you hear a clap or an explosion goes off, it basically sends a pressure wave, and your eardrum picks up on that pressure wave, and that's what we perceive as sound. So everything ahead of this wave, this is called a shock wave. And this is so if you're just traveling the speed of sound, you get something called a normal shock wave, meaning that it's just this wall in front of you. As you travel faster than the speed of sound, the shock wave starts to bow toward your vehicle. So if you're traveling very fast, you're going to get a shock wave like this. So basically, the shock wave separates two regions of the surrounding atmosphere. So in this region, we'll call region 1, everything is like you never even showed up. So the pressure, density, and temperature of region 1 is just the regular peaceful day ambient condition. Now you're coming and you create noise, which creates a change in pressure, density, and temperature. If you're traveling less than the speed of sound, those changes in pressure, density, and temperature can propagate, just move forward, move forward, move forward ahead of you, and they propagate upstream. However, when you're traveling exactly at the speed of sound, all the noise that you emit is trying to move forward, but you're going the same speed as the noise itself. So all of that noise just stands right in front of you and basically creates an imaginary wall. And this wall represents a discontinuity in the thermodynamic properties of the atmosphere. So sudden change in pressure, density, temperature, and there are other thermodynamic quantities that change as well, enthalpy, entropy, things like that, which we want to get into. But basically you have one pressure on this side of the shock wave and a separate pressure on the other side of the shock wave. So that's what a shock wave is. It's a little bit of a background. So we have a wave angle of beta, and suppose our speed is given by a Mach number, so Mach m. So Mach number is basically the ratio of your speed by the speed of sound. So Mach 0.5 means you're traveling at half the speed of sound. Mach 1, this is why I drew it on here, Mach 1 is at the speed of sound. Mach 2 is twice the speed of sound. Mach 3, you're traveling 3 times the speed of sound, and so forth. I mean, some aircraft can go Mach 5, Mach 6. It's pretty amazing. Also, when the space shuttle returns, when it used to return, I mean, you have very high Mach numbers. I would at least Mach 20, I think. But space shuttle, the Apollo missions, when they came back in the capsule that entered the atmosphere, outside of the vehicle, and remember there are actual people in this vehicle, but outside of the vehicle, the temperatures are so hot that the actual molecules of the atmosphere dissociate. So instead of having oxygen molecule O2, you get 2 oxygen atoms. So it's so hot that even the atomic bonds that form the molecules can't stay together. So it's a very exciting, dynamic process when you come in at those high Mach numbers. So then air or fluids in general have something called an adiabatic index. Gamma. And so gamma for regular air is 1.4. So I believe the adiabatic index is a measure of the change in specific heats, but it's a thermodynamic constant for different fluids, so we'll just treat that as a constant. So in this problem, we're going to take a look at the density ratio. So F So we're going to take a look at the density ratio. So F of m is given by gamma plus 1 m squared sine squared of beta divided by gamma minus 1 m squared sine squared of beta plus 2. So this is derived in, a advanced thermodynamics class for, compressible fluid flow, or thermodynamics compressible fluid mechanic type course that you would study shock waves and things like this. So this is the density ratio as a function of the Mach number of the aircraft. So this tells you the ratio of the density in region 2 divided by the density in region 1. So it tells you multiply this ratio by the atmospheric ambient density to figure out what the density is on the other side of the shock wave. So across the shock wave, you get a sudden change in density. So for example, if you have, let's just plug in a number, if you have a 45-degree shock wave, so sine squared of 45 degrees is 1/2. So we get 2.4. Let's say we're going into Mach number of 2 times 4 times 1/2, and then divide that by 2 plus 0.4 times 4 times 0.5 about 1.7. So basically the density increases by a factor of approximately 1.7. So if you have a certain atmospheric density, it's almost twice as dense on the other side of the shock wave. Remember, this is a discontinuous jump. So you have one density and then pow, another density. So it's an abrupt change in all of the thermodynamic conditions of the air. And also these shock waves are what create sonic booms. So I said earlier that we perceive sound because sound is a pressure wave that travels through the air. Here you have a very strong pressure wave, and when you're on the ground, when that shock wave passes over you, you get a sudden change in all of the pressure, which you hear as a loud boom. It's called the sonic boom. So the sonic boom can even be heard from the ground. I was in Florida once when the space shuttle was returning, and when it flew over Orlando, you hear the loud bang, and then all the car alarms in the block go off just as the space shuttle was returning, because it was still traveling faster than the speed of sound. So about a 2 times increase in the atmospheric density if you're going in Mach 2. So with this, one thing we can look at is, so some of this is a review, limit as m goes to infinity of f of m. Well, beta and gamma are parameters. So right now we're just viewing them as a constant. So beta is a constant, gamma is a constant. This is no different than saying, what's the limit as m goes to infinity of am over bm plus 2. Well, it's just going to be the ratio, or am squared. Right? So we have a rational function. We have an equal power in the numerator and denominator. So we have a quadratic in the numerator, quadratic in the denominator. So in the limit, this is just going to approach the ratio of the leading coefficients, so a over b, or in this case, gamma plus 1 over gamma minus 1. And it's literally gamma plus 1 times sine squared beta over gamma minus 1 times the sine squared beta. But the sine squared betas cancel out, so the limit is just this ratio, gamma plus 1 over gamma minus 1. So that means gamma plus 1 is 2.4 divided by 0.4. That is, for air, it's going to equal 6. So that means as you go faster and faster, there's a theoretical limit on how big of a difference you can have in density. So as you approach, in the limit, as the speed, the Mach number goes to infinity, you're going to level off at a 6-fold increase in density when you move across the shock wave. So the density upstream is going to be 1/6 of the density after the shock wave. Let's see what we get at Mach 10. So at Mach 10, we have 100 times 0.5 times 2.4, and divide that by 2 plus 100 times 0.5 times 0.4, 5.45. So at a speed of Mach 10, your density ratio is 5.45. So it's already fairly close to this limit. And so going Mach 10 is pretty fast, and you're at about a density ratio of 5.45. So next, we're going to take a look at the pressure ratio. And we're going to use the limit definition of the derivative here. So here, we'll say g of m, so it's a little bit of a different formula. It's 1 plus 2 gamma over gamma plus 1 times m squared sine squared of beta minus 1. So this is the pressure ratio. So it's the pressure in region 2 divided by the pressure in region 1. And so first, let's actually calculate g prime of m using the limit definition of the derivative. Now here, we want to treat everything else as a constant. So beta and gamma are constants. So we start off by just writing limit as h goes to 0, g of m plus h minus g of m over h. Right, so this is just the limit as h goes to 0 of this difference quotient. Difference quotient just means a quotient of two differences, change of g divided by change in m. So it's delta g over delta m. So this is going to look like the following. Limit as h goes to 0, 1 plus 2 gamma over gamma plus 1 m plus h squared sine squared of beta minus 1, and then minus 1 plus 2 gamma over gamma plus 1 times, I'm going to continue on the next line, let me try something. Haha, perfect. Okay, I don't need to continue this on the next line, so times m squared sine squared beta minus 1, and then all divided by h. Now let's set up our game of war. So with all this limit definition of the derivative, we write down our thing, see what cancels, simplify, take the limit. So first of all, I have 1 minus 1. So this cancels with that. And then also, this times the minus 1 minus this times the minus 1. This minus 1 cancels with this minus 1. So basically, the 1 minus 1 cancels here. The same coefficient factors in. So when this factors into that sum, same thing happens here. So I have minus this minus negative that, and those two cancel. So what we're left with is this coefficient times sine squared beta times m plus h squared minus this coefficient times sine squared of beta times m squared. So basically we're left with, since this coefficient and the sine squared of beta are on both terms, I'm going to pull them out. 2 gamma over gamma plus 1 sine squared beta times the limit as h goes to 0. M plus h squared is m squared plus 2mh plus h squared, and then minus m squared all over h. Now you'll notice next the m squareds cancel, and then I can take, since both of the terms remaining in the numerator have a factor of h, I can pull out a factor of h and cancel. So this h cancels, and then one of these factors of h cancels. So I basically get this times the limit as h goes to 0 of 2m plus h. So this essentially becomes no, that's okay. Let's just make some space up here. So I think we're done with this. So basically what we've showed was that g prime of m is equal to 2 gamma over gamma plus 1 sine squared beta times the limit as h goes to 0 of 2m plus h. Now, as h goes to 0, this is simple. H just goes to 0. 2m is a constant. So this whole limit, we get the following. I'll write it up here. So g prime of m is just 2 times 2 is 4. 4 gamma m over gamma plus 1 sine squared beta. So that's the derivative, just like that. And when we learn our derivative rules, it will be even easier to count because we won't need to always rely on the limit definition of the derivative. But for now, you can see how that gave us this derivative. So next, let's calculate g of 2. So g of 2, if gamma is 1.4 and beta is 45 degrees or pi over 4 radians, so sine of beta is 1 over square root of 2, sine squared of beta is 1/2. So, and the Mach number is 2. right? Because we're doing g of 2. So g of 2 is going to be 4 times 1/2 minus 1 is 1. It's easy enough. 2 times 1.4 divided by 1.4 plus 1, 2.4, is 1.16666 and so forth, or 7 over 6 plus 1 is 13 over 6. So g of 2 is 13 over 6, or approximately 2.166 repeating. So over a 2 times increase in pressure, so the pressure ahead of the shock wave is only half as the pressure behind the shock wave. And also, let's compute g of 2.1, because what we're going to do next is we're going to compute the exact value of g of 2.1. Then we're going to approximate g of 2.1 using the derivative and the value of g at 2. So we're not going to use the exact value, but we'll approximate g of 2.1 using the derivative to see how closely we get. So the exact value of g of 2.1, so we can plug in 2.1 for this equation. So we have so starting inside, 2.1 squared times 1/2 minus 1. I get 1.205. Multiply it by 2 right here. Multiply it by 1.4. Then divide it by 2.4. And at 1.4058, I add 1. So g of 2.1 is 2.4058333 repeating. So we can actually, without knowing the value of g of 2.1, we can use the derivative to approximate it. So g of 2.1 is going to be approximately g of 2 plus g prime of 2 times the change in, so times 0.1. Right, so this represents, g of 2. This is change of g over change of m times the change of m. So this whole thing here tells me the total change in the output. So it's g at 2 plus the change in g, approximate change of g, going from a speed of 2 to Mach 2 to a speed of 2.1. So this is going to be the previous result, 2.166 repeating, plus g prime. So I'm going to have to evaluate g prime of 2. So 4 times 2 times 1.4 divided by 2.4 times 1/2. G prime of 2 is 2.33 repeating. So 2.33 repeating times 0.1, and now I'm going to add that to 2.166666666, and I get plus 0.233 repeating, and that gives me 2.4. So my approximate value of g of 2.1 was 2.4. So what I did was I used the derivative, because remember, the derivative tells you how quickly g, the function g, is changing for a change in m. So this is really the local linearization, or the tangent line approximation. Local linearization, tangent line. Because the whole idea behind this is that we're treating the function g as a straight line near the point 2, right? So we're taking the output at 2, and we're adding to that the slope times the delta x. So if you just think of, y minus y naught is equal to the slope times x minus x naught. This is the point slope. Well, y is going to be the initial value plus the slope times the change in x. So here the initial value was g of 2. The slope of the tangent line is the derivative, so g prime of 2. and then the change in the independent variable, in this case a change of m, is just 0.1 because my independent variable is going from 2 to 2.1. So my change of m is 0.1, my slope is the derivative, and I add that to the starting value, so the starting value of g at the point 2, and I approximated 2.4, which is pretty close because the exact value of this equation for 2.1, m is equal to 2.1, is 2.40583333. So I'm, less than 0.006 off. So pretty close approximation to the exact value of 2.1.